into different modes. In Wedge 100, we support 5 different modes: 1 by 100 gig mode, 2 by 50, 4 by 25, 1 by 40, and 4 by 10. For 100 gig mode, usually we use it as an uplink to our fabric switch. The QS, for example, we use the CWDM for optics. Right? It's for the uplink to the aggregation switch. For 2 by 50 gig mode, right now our Yosemite server have a 50 gig NIC. 50 gig NIC. So the downlink from the Wedge 100 to the server, we use the dark cable to break into use the white cable break into 250 gig and connect to the Yosemite CX4 NIC. 4 by 25, the same thing. Some of our server use 25 gig NIC. It's SFP28 form factors. We use the breakout. We call it fan-out cable. Connect to those NICs. 40 gig and 4 by 10 gig as for the previous generation backward compatible because we still have some old servers we need to connect. So it's a very flexible, multiple generation of the NIC we can talk to. It's possible maybe in the future we have a 100 gig NIC, right? Downlink to use the DAC cable. 100 gig optic transceivers. Wedge 100 support the QSP28 100 gig optics. We select CWDM as our standard in MSA for optics. Electrical interface is the same, it's just for the RWE call E4 standard. We can support any other MSA such as SR4L4, CR4. But CWDM is our choice, it's our standard. It also backward compatible support all the 40 gig QSP plus optics like 40 gig SR4, which use a lot in the standard. And 40 gig AR4, we also use a lot in the standard. Dark cables. For QR connection to the server inside the rack, because the distance is short, it's like maximum. Our rack is about 2 meters high, so the cable maximum could be 2.5 or 3 meters. We use 3 different type of cables. QSP28 100 gig to QSP28 100 gig interface. They have a 1 meter, 2 meter, 3 meter. And QSP28 100 gig to 2 QSP28 50 gig cables. We also support 1 meter, 2 meter, 3 meter. And the last cable is like 100 gig to 4 SFP28 25 gig cable, 1 meter, 2 meters. Of course, we support the old generation of 40 gig, fan-out cable and 40 gig cables. This is the Q2Q cable, 100 gig to 100 gig. It's possible in the future we have a very high bandwidth servers. We need 100 gig uplink. It's possible we can use this cable. This system has no problem to support up to 3 meters. This is a Y cable because there's no formal mechanical form factor for the 50 gig Ethernet. So we simply use the QSFP form factor, but only 2 lengths used. So you see the pictures on the left side. That is I call it the YN. YN is all the 4 lengths used is 100 gig 4 by 25. And the right side is only A and B N. Each QSFP only have a 2 lengths used. That's 50 gig. We use this Y cable connect to our Yosemite 50 gig. This is the last cable is fan-out cable is 100 gig to 4 by 25 fan-out cable. For the previous generation 4 by 10 gig we use a lot. This cable just upgrade version. Try to have speed to 25 gig. We have some servers use 25 gig, then we use this cable connect. I think that's all from me. So here is our OCP contributions. I think Omar yesterday uploaded the design package, including the Sixpack specification, design package, Wedge 100 specification, and the design package uploaded to the OCP. We try to make this public and think in the near future, anybody can order this switch from our ODM partner. The following is the link of the OCP spec. So that's all from me. So any questions? L4 is from yeah. No, data center is it's possible. We have not tested that. I mean, data center is all front to back.
Any other questions for GP?
Is there any ETA for the 100 gig six-pack switch over here?
We are working on the next generation 100 gig modular switch, right?
What was the question?
The next generation 100 gig modular switch. It will be so much.
Haven't announced anything about it, but stay tuned.
Never soon enough.
I think it is amazing how quickly things are changing, in terms of, Wedge 40, now Wedge 100. I think yesterday we talked about it being 100 gig data centers anyways. And there's a lot of stuff that we covered yesterday in terms of what you have to do to get a 100 gig data center out. 100 gig optics, being covered, 100 gig servers, 100 gig switches. So we're in the middle of that transition. We're just starting off it. All right, so this is Haney from the data center network team.
Hi everyone, I'm Haney Morsi. I'm part of the team at Facebook, the data center network engineering. The team that is responsible for designing and deploying Facebook data centers around the globe. So today I'm going to cover how we tested Sixpack in our data center environment to make sure that it fits our data center requirements. The three areas that I'm going to focus on are
Is that better? Not for me.
Can you give me better now? All right, great. Okay. So I'm going to talk about Sixpack testing. So first, I will start with where Sixpack fits in our data center and how we tested it, the test topology that we used, and the different testing areas that we have covered. First, I'm going to start with a very brief history of Facebook's data center evolution. So we started with a data center design called the cluster, and we evolved from there to another design that is more flexible called the fabric. So here's the cluster, and here in the cluster you see that the cluster consists of a relatively large number of racks or RSW, we call them the rack switches. We're talking about several hundred of rack switches in a cluster. Each type of rack serves a rack of servers, 10 gig servers in this design here. And uplinks into our cluster switches, these CSWs, using 4 10 gig uplinks. This is called a 4-host cluster because, as you see, it contains 4 cluster switches in the cluster. So it's a 4-host. This is the cluster design, and because it was relatively large, these cluster switches were also like the largest switching platform that you can find in the market. So that presented some challenges because only few options of that large magnitude of the switching platform, and other problems with complexity of the switch design, and the other disadvantages that actually led us to move from this data center design to the fabric. one of the biggest problems with the cluster is the ability to grow. And the growth in growing in a cluster is very difficult because you are limited by the capacity of the cluster switch. So pretty much if the port availability is over on a cluster switch, there is no more room to grow in a cluster. I already talked about the cluster switch complexity as a very large, huge switching platform, which brings with it architectural complexity and makes it hard to operate and control. There is also a problem here when you lose one cluster switch out of the four, you immediately have lost 25% of your cluster bandwidth, right? Also, that kind of large cluster switches bring a problem when you want to have more bandwidth per rack. Because these larger, very dense switches do not really catch up with higher speeds as fast as smaller switching platforms. The oversubscription also here is a big problem in clusters, and we improved on that with the fabric. So let's move actually to the fabric to see how the fabric is different from the cluster here. So this is an example here of a server pod. This is also 4 posts. It looks very similar to the cluster, right? Except that the size of this server pod is much smaller. So a typical number of total racks that we would use in a server pod is 48 versus a number of several hundred total racks in the cluster. Here also the fabric uses 40 gig of links, so that's an automatic upgrade in bandwidth per rack. Just by looking at this, you might wonder, I'm not seeing much difference between the server pod and the cluster, but actually the difference comes in first of all in the size. Here this is a small unit, a small building block in the fabric. It's a repeatable unit, and also difference comes in the upper tiers or the aggregation tiers that come after that between the racks and the top aggregation layer. Here's a complete view of our fabric. Looks a bit complex, but it just demonstrates the different screens that we have, the different tiers that we have in a fabric. So we have the server pods, as you see at the bottom right here, a number of them, and many of them, and these are aggregated by what we call the spine planes that go orthogonal to them, right? And another layer above that would be our edge pods, which takes you out of the fabric to other fabrics or to the users, actual users on the internet. Actually, if you look at this actually looks like a really large switch itself. Like it's mimics an orthogonal design of a large switch where the server pods look like the line cards, the spine planes look like the fabric cards, and the edge pods here look like the uplink line cards. So what we got here by using fabrics instead of evolving into fabrics from clusters is a lot of flexibility. Growth has become much easier. If you would like to grow to meet increased intra-fabric bandwidth, you just add more spine switches in the spine. And if you would like to grow to meet increased external traffic that is going to other fabrics or to the internet, you just add more edge planes. So this is actually what I wanted to get to. Is from this introduction is where the Sixpack fits into our data center. And the current target for Sixpack is as a fabric switch, they're using the server pod. Future targets will be in the fine plane as a fine switch, and in the edge pod as an edge switch. So the fabric switch, which is the initial target for the Sixpack, what do you expect from a fabric switch? So basically, as you see here, as we saw here, the fabric switch in the server pod pairs with the rack switches underneath, and pairs with the spine switches above it. Those pairings are using BGP. Also, the fabric switch heavily uses BGP policies to control route advertising. It aggregates traffic from all rack switches, and it load balances that traffic across all spine switches in the spine plane. And one expectation of the fabric switch is to react very quickly to failures. And all these expectations and requirements are imposed on the Sixpack as well in that role. These are the tools that we have used for testing Sixpack. Effectively, we expect a traffic generator, route injector, collecting statistics, dashboards to monitor such things as CPU loads, interface errors, and so on. Automation scripts to do the kind of tests that are repetitive in nature. And very importantly, also comparing with an established vendor platform to see how we measure up. This is a test topology, just to give you an idea how it compares with an actual data center, an actual production data center fabric. So the difference here is we just used 2 pods. In production, we have many more than that. Each pod is 2 posts, so just 2 SSWs. In production, typically we deploy 4 SSWs, so it's 4 posts. Since it's only 2 posts, we use parallel uplinks, 2 parallel uplinks from each RSW to each SSW to make up for 4 total uplinks, just like in production. The spine planes, as you see here, include only 1 SSW. This is definitely different from production, where our starting point is 12, which gives you 4-to-1 over subscription ratio. So in order to simulate a full capacity fabric, we run 48 parallel links between the fabric switch and the spine switch. The XA configuration, as you see here, the XA is right in the middle, right? What the XA is doing is it injects routes to test scale into the Sixpacks, and it also injects traffic. So it simulates actually servers behind the hub rack, so the RSW in each pod. It simulates 50 servers behind each RSW. So the testing areas, these are the areas that we have tested. We have covered functionality, we have covered the failure. We wanted to definitely check that the system will recover under different failure conditions. Scale, stress, integration with our tools that we use to manage and monitor in production. Performance testing, very important for us, and longevity, just to let the traffic run for an extended period of time. Here's the functionality testing. We would check, verify the BGP peerings between the Sixpack and the RSWs. The BGP peerings between Sixpack and the SSW, and the internal BGP peerings between the FCs and LCs. And these also run BGP to exchange route information. We would test ECMP across all parallel links. routing policy, of course, that controls the distribution of routes, and the graceful restart as well between the Sixpack and the RSW. Here's a sample output for a BGP peering between Sixpack and the RSW, just for the technical folks here, something that you can relate to. You see, we have two BGP sessions on each lane, one in each address family. And here's also another output sample that shows you the internal peering between the LCs and the LC. So this is from the perspective of one LC. You see it formed 4 internal BGP peerings with the 4 fabric parts. Again, one per address family to each fabric part. As for testing failure conditions, OIR, online insertion and removal, so we want to test the recovery of all system components. So we start by the interface recovery. What happens when you shut an interface in software? Shut unshut. What happens when you pull a fiber? What happens when you pull the optics and the fiber together? So all these kind of tests to confirm the recovery of the interface. At the line card level, similar kind of also failure testing here, rebooting the LC or physically receiving the line card. Same thing with the fabric card, very similar, rebooting and receiving. Also a more failure tests at the process level, like killing and respawning the BGP process or the agent process. And finally, a failure test for the whole system by rebooting the whole system in software or physically. The scale and the stress testing here, basically, as I hinted out before, we are using Ixia to generate a large number of BGP prefixes to test the scalability of the platform. So as you see here, we generate 8,000 V4 plus 8,000 V6 BGP routes from Ixia. We run different types of traffic concurrently, all at the same time. And the different types of traffic here mean the intra-pod traffic that goes from basically a server to a rack switch to reflects off the Sixpack, goes back to another rack switch in the same pod, right? So it's intra-pod. And then from there goes to the destination server. So that's intra-pod. There is also inter-pod traffic that leaves the pod altogether, goes to the SSW, and then from there goes to another pod. And there is external traffic that's in US internet traffic or machine-to-user traffic as we call it. Part of the stress testing here is, if you notice the little flattening that happens over there, that's like flattening the 16,000 routes every 60 seconds to test how the Sixpack will hold with that kind of event. And that is the kind of test that we do to find such things as memory leaks, for example, as this operation can, leave some memory space unreleased. Also, we do high frequency interface shots, shut-no shots, and the same thing with BGP. BGP is also we shut-no shot these for fast and for an extended period of time. This is also part of the testing here is to make sure that the Sixpack will be managed and monitored, same as a vendor switch in our environment. We rely heavily on automation to operate our production environment, and we want to make sure that Sixpack meets those requirements and can be easily managed like a vendor platform. Performance testing, very important component for us. We want to make sure that the Sixpack will react quickly to failures and will not cause excessive drops in case of any failure. So These are different types of failures that we have measured. Like for example, interface when an uplink goes down from an RSW, how much traffic we're going to lose. So that's what performance testing is focused on, is measuring the impact. Here's an example for how much traffic was lost when we lost an uplink from an RSW. And as you see here, the amount of traffic that was lost, for example, in the inter-pod traffic, translates to just very few number of milliseconds. So this reflects a quarterly action from Sixpack in this kind of failure. And my colleague Jasmeet is actually going to elaborate on this further, how we were able to get Sixpack to drop that very little number of packets by not waiting for the routing process, for the routing module to update the hardware. Finally, this is the longevity test, and basically what happens here is we let the traffic run with the full traffic scale for a very long period of time, and what we look for here is the stability of the system as a whole, the continuity of operation, and basically it gives us confidence in the platform for the long term. Automation is a very important piece of any testing because it allows you to do the kind of operations over and over and for so many times, such as shut-in, no shut-in interfaces, same thing for BGP neighbors. Some of these operations are expected to be hitless, like the software-driven operations are expected to be hitless, like shut-in, a BGP neighbor should not trigger any packet loss. Reloading LCs constantly, FCs doing drain, undrained. This is a very important also component here for us in the data center, is to be able to drain a switch to perform any kind of maintenance on it, and then undrain it back. So testing automation helps us actually do this kind of repetitive kind of testing over and over. And we have a goal to automate all the kind of testing that I have covered. So this pretty much concludes how we tested Sixpack in our environment. And if there are any questions.
The Sixpack seems to be a 128-volt switch, but you only seem to be using 96 volts in fabric.
That's correct.
Is there any particular reason for that?
Yes. So the question is from the slides, it looks like we are only using 96 volts, which is so there is one MC line card, and that's actually intentional for the fabric switch. That's the capacity that we use. We use 96 ports on a fabric switch. We do not use the bottommost line card. 48 ports go to the RSW, and 48 ports are available for SSW for what we call a non-blocking configuration. So the oversubscription is, there's no oversubscription in that case, it's 1-to-1. So yes, the reason we are doing this is FSW functionality only requires 52 line blocks.
All right, so we're gonna switch over to John. Thank you, Hank. And I'm gonna switch over to John. He's on the software team, and we'll go over quickly just sort of some of the challenges around FLOS and Wedge.
Hi, I'm Jasmeet Bhagat. I'm a software engineer at Facebook, and I'm going to be talking about Facebook's software switch development. So, brief outline of the talk. I'm going to first talk about our Wedge top rack switch. Then I'm going to talk about evolution from the top of rack wedge switch to the Sixpack, how the software needed to be evolved and scaled out. Finally, I'm going to talk a little bit about the FP development methodology, what principles guide us, and how we develop the software. There is a lot of content here. I do also have a lot of links at the end to follow along for more material. So with that, let's go back to 2013. 2013, we started deciding that we'll build our own top of rack. Our motivation for this was multifold. First, we realized that we don't use all the features that are available in the embedded switches. The number of features that we use on our top of rack switch are a handful. And we believe that we could make our software, write our software, just satisfying those features in a much more scalable and robust manner. But then also with that, we could also move faster on the desired bug fixes and features that we do require. And we don't have to wait for vendor development cycles, which can last a long time and keep us less slow stuff. Next, we could also, there's a lot of talk of SDN with the wedge switch. We actually could go even beyond that, or even beyond the open flow specification. We have an API that we expose via script, which is our IDC mechanism. We could choose to expose whatever functionality we wanted to expose to all the controller applications. Finally, as a design principle, we thought we'll be very careful in building this as close to be as a server as possible. This way, we could use all the goodness and all the tools that we have for managing our servers or monitoring our servers. They would work from day one on the wedge. And this turned out to be a big decision because now not only do we could run off the ground very fast, we continue to get benefits as those tools evolve and as all of the Facebook works on improving those tools with monitor and manage servers. So with that, just to make it concrete, let's see how closely we actually came to making it look like a server. This is the Facebook server. There is an x86-64 microprocessor. There is the BMC system on chip for monitoring the environmentals. There is the OpenBMC library, BMC software there, which interfaces with the BMC chip, which also, by the way, is also in open source. The software for this is freely available. There is the standard Linux kernel. There are system tools and libraries, and then there are Facebook-specific monitoring daemons and config management. That's the server. Let's look at Wedge now. When you go from a server to Wedge, only a few things get added on. A Broadcom Client 2 ASIC, which is a peripheral, the OpenNSL library, which the Broadcom is a source for talking with the Client 2 ASIC. There is the AirBoss agent, which talks to the ASIC through the OpenNSL library and does all the ASIC programming. And there is the routing daemon, which for us right now is BGP, but could be anything for everybody else. The communication between the routing daemon and the AirBoss agent is via script again, so reuse there as well. And the routing daemon implements the protocol and tells the AirBoss agent what route to program and remove. So that's it. That was the difference. With this, we could start leveraging all our tools, all our monitoring tools, and get the system up and running in a quick time. The Wedge has been a phenomenal success. This is a chart of number of wedges in production. It's plotted over time. The number is into thousands. So a good chunk of Facebook's traffic is now going over the wedge switch. What does that mean? All the OCP posts, there's a good chance that those are going over OCP wedge switch. There was a long, while I said we could get there early on, there was a long way still to sort of mature this platform. And we've written about what our experience was in sort of getting this scalable and in production. Some of the interesting problems that we saw was as we reused a lot of the Facebook software, when problems occurred, there were circular dependencies because we were using Facebook software that would depend on servers which were behind top of rack switches. And we would get into problems that way. So we had to carefully engineer about how we manage those. Another thing that we also had to take time and improve was our hitless upgrade. We were very clear from day one that we wanted to upgrade these switches at a very fast pace, push out new software on a very good cadence. It took us some time to get this right in our today. And we've written a lot about this to summarize our experience. From there on, we decided to go up to the next network layer. we started to start, not just stop at the rack switch, but to rather start moving up in the network layer. So here is a diagram of our fabric. The bottom of this is the top of rack wedge switch. The next layer switch, which we call the fabric switch, which Hanif also described, we started to tackle that. The Sixpack would be the one fitting there. The challenge we set ourselves in software is that the software is right for Sixpack. We should also be able to very easily extend that to the next layer switches of model, the spine and the edge switches, which are even bigger switches. So that's good for motivation, but let's take the lay of the land. Speaking of, from a chassis switch point of view, the rack switch is a relatively simple device. When you go to the chassis switch, the complexity and scale explored by sometimes even more than an order of magnitude. So in our case, just to look at some numbers, the routes on a rack switch are typically of the order of 1,000. While for the Sixpack, they were benchmarking to 16K routes, possibly on each line card. The failure domain of a rack is, well, a rack. If a rack goes down, that the servers behind that go down. Failure domain of a Sixpack is about 48, or in sometimes even more than that. The traffic that's traversing a wedge is 640 gigabits. The traffic that's traversing Sixpack is up to 5.1 gigabits. That means that all the work we did for any service update, any millisecond outage here would be much more noticeable than on a wedge. So we have to get this even better. The BGP pairings go from 4 to more than 100. So what's the conventional way of building these switches? Over the years, the conventional way of building these switches has been to have a supervisor engine which serves as the brain of the system, and then there are a lot of set of line cards which serve as dumb forwarding devices. The supervisor engine implements all the intelligence, all the routing protocols, and tells the asset basically what to do. So there are also, hot standby conditions where two supervisors are used for failure when one fails over the other should speak. We didn't go this route. To us, a switch, Sixpack is just a set of edges connected together. Each of them is an individual system. We don't distinguish them. Each of them has a microprocessor. Each of them has an ASIC. Each of them is essentially a wedge, and the Sixpack is a set of edges connected in a particular topology. Interestingly, the internal topology of the Sixpack looks very similar to the external topology of our fabric. There are in the Sixpack there are line cards which connect up to fabric cards, and in the outside there are rack switches which connect to core fabric. What that means is we could take our web software and immediately start working on it and start leveraging that and start running it. We didn't have to build a more, a separate software layer which would be talking to all these benefits. What that also means is all the monitoring solutions that we have, all the management solutions that we have, would manage these individual systems individually. The systems that monitor link health, for example, would now also look inside the Sixpack and find out if the links inside are having a bad time or something. However, philosophy, that was for the philosophy side. That was, saying how we will build it. That was an architecture philosophy concept. There were several challenges as we started digging deeper into the problem of getting this to actually work. And I'll just show some highlights. So the first thing we saw was, looking at the 16K route with half of them V4 and half of them V6, and looking at the Trident 2 ASIC specifications and the TCAM entries, there was no way that these routes are going to fit in the TCAM entry. So what do? Well, we started looking at the chip specifications and seeing how we could optimize. There are a few features that in Trident 2 that help us here. There is the uniform forwarding table feature, which lets you partition CAM and TCAM in a certain way, so you can use certain portions for certain things. There is ALTM also, which actually we did not use, but we plan to explore in the future maybe. And then a key feature of Trident 2 was that it allows you to put host routes, even when they are TCMP, into the CAM. So you can use the TCAM or the FIB for really the LTM routes and not waste all that space in the host route. Looking at our route distribution, there are a fair number of host routes because of all the virtual IPs that keep floating around. So with this, we built an optimization where you could actually program the host routes in the CAM and keep all the the LPM routes in the fib. And with that, we could fit the 16K route. The interesting challenge also came here. How would you want boot on doing service upgrades across this transition? But we could be actually measured this, and it was hit test as well. So the ones that are now this optimization applies on wedges as well, and we've transitioned successfully from having all the host routes in the CAM to all these searchability features. The next, we were now able to fit the routes, but when we started measuring the performance, it was terrible. It would take up to 5 minutes to program and unprogram the 16K route. The CPU at this time would be pegged. That would cause the dearing to flap, then to further flaps, and churn and churn and churn. So, so what do we do? At this time, we started reading, that in the industry, there are people have used, this has been a big problem. People have actually used FPGAs to speed up route programming, and we were at this point wondering if we missed a hardware breakout. However, at this point, it was simply too late. We couldn't redesign the system from the hardware perspective. So we started doing what we know best, optimizing software. We started profiling and improving our software, and then simply recognizing that we made some trade-offs on the rack switch, and because of the low scale of routes there, we just don't notice the performance. Just by optimizing the software and iterating over this multiple times, we are now down to 5 seconds, which is actually benchmarked to several vendor performance, and we get the similar numbers. Most of this time is actually spent in programming the app. The software time is very short. So then we noticed what on the Sixpack was you saw the sample topology. The Sixpack was connected to wedges. So there was wedge which was connected on the uplinks to the vendor switch and to the Sixpack. You noticed an interesting problem. The wedge would ECMP its traffic perfectly. However, the Sixpack from all its uplinks would utilize only half its uplinks. Now, also interestingly, if you took the vendor switch out of the production, Sixpack would start using all its uplinks perfectly and staying traffic perfectly. What was going on? Well, remember I said, they're running the same software, hence they're running the same hash function. And this is a classical problem in switching. If you change to hash function, you get poor utilization on the next big above, and this is called hash polarization. What we now have is a different hashing function at each of the layers, so that ECMP gets spread across evenly. Finally, our mandate was that if a link or line card or even a Sixpack fails in a fabric, nobody should notice, as long as there was spare capacity. However, when we first measured this, with our 300-second route programming, the instability would last for up to an hour. So this was certainly something wrong. Even with our optimization in our routing, we were able to get to between 5 and 10 seconds, but it was not predictable. So what was going on? At this point, we started to look at the system view of what happens when a link fails and what we can make better. So what was happening was when a link failed, the FOS agent would notice, tell the routing daemon, hey, link 1 and 2 are down, and imagine all these links are part of an ECMP group, so traffic is being sent on across these links. The routing daemon would churn on it, optimize its routes, and send a message back saying, hey, these are being routed, remove them. However, all this time, the traffic is flowing and packets are being lost. But once you look at it this way, the solution almost becomes obvious to you. Why wait? Just when you get a link failure, just prune the links of the block, asynchronously to the sending of message, and you stop the bleeding right there. So with this, the messages still go, the routes still update, but at this point, the message is only about software update. The traffic flow has already been stopped. With this, we are down to a few milliseconds of failure, subject to how fast we can detect links, which also we can tune to our liking. With this, let me turn to the final part of the presentation, where I'll speak briefly about the Facebook development philosophy and methodology. So what you see often in the industry is what is called what you see a picture here. There are two sets of people building systems and using systems. One is the development, which works on the software and build systems that operational folks later use. The problem with this is that the development people do not see the pain of running a system day to day, and do not know what the pain points are, do not know what to optimize, do not know what to fix. The second is the operational folks, on the other hand, do not know the internals of the system, so they can't really go and immediately fix the problems that they are facing. They keep going back and forth to mature the system, and this takes a long while. The second problem that is happens here is the development cycle is typically 6 months to a year of developing, then some amount of QA, and then the software goes on. Then this feedback cycle of what is working in production and not is very long. It can often take between a gap of a year to a year and a half of realizing what did work in production. We don't have that problem. Since we run our own infrastructure, we have something called what is called DevOps in the industry now. We keep development and production very closely tied. Developers have direct access to our network, and in fact, they are the first point of contact when things go wrong in the network. That way, they understand the production environment very well, and they build software to make things better for their own lives. And they react to problems, and they know how to fix it, and they know actually what the problems really are. Also, I've talked about long feedback cycles. We try to keep this very short. We have institutionalized a mechanism of trying to push new code out every week. So we keep our code fresh in production. We do have a method of building a lot of unit tests and building a lot of integration tests, and also sort of have a methodology of how we push the code out so that it first hits a set of lab switches, then a set of switches which can take failure, and then only the wider world. But with this, we are very careful of pushing out code as soon as possible. So we really know what works in production after we build and after we pass all these tests. So just
I think we got
okay. So this is the last slide. What we've done is build simple and reusable components, iterate fast to make them bulletproof, and reuse to build bigger. There are some links here. I'll take it.
Thank you. So while we swap out, we can take like maybe one quick question while we swap stuff. Thanks guys for coming, and thank you also to Big Switch for. We chatted a little bit beforehand. You said you accommodate a little bit of delay. Thank you very much. Any quick questions?
I have a quick question on the hash polarization. You said you use different hashing algorithms at each layer. Was it just like a constant that you added? So rather than hashing like 0 through 4, it would be like 2 through 0.
So actually, we started hashing differently on so.
So with the Tomahawk, you have